Okay, yeah, second video in this section. This is 6.7, but closely related to what we just did, 2% composition. So I am going to do them both at once for a little bit of ease here. So we're going to talk about what we call empirical formulas. And we'll get to the kind of definition shortly. But it's the lowest number. Actually, I'll do it right now. It's the lowest whole number ratio of atoms in any compound. That's the the empirical formula. So we learned how to do percent composition just a little bit ago, and percent composition is great. However, multiple compounds, because all the compounds are made of the same atoms, right? So if you talk about hydrocarbons, carbon, hydrogen, oxygen, eventually you're going to have overlapping chemicals that have the same percent composition by mass. So for example, one is called methanal, which is CH2O, and another is called ethanoic acid, which is C2H4O2. So totally different chemicals, different properties, different applications, got to be treated differently, but both of them have the same percent composition. 40% carbon, 6.7% hydrogen, 53% oxygen. That's the one that we just looked at. So those would both be. So when I have that, that could be methanol, it could be ethanoic acid, it could be either one. So it's in some circumstances more than others. It's very important that we know which of these compounds that we're working with. So the best way then to do it is now that we know about percent composition by mass, we have to be able to find its chemical formula. And those subscripts in the chemical formula are going to tell you how many carbons, how many hydrogens, how many oxygens. For example, the first one has 1 carbon, 2 hydrogens, 1 oxygen. The second one has 2 carbons, 4 hydrogens, 2 oxygens. So a little bit different. So what we're going to look at, it doesn't matter the sample size of each one, because if the percentage, so it doesn't matter if my test is out of 51 or 89 or 211, right? If you got 40%, you're always going to be 40%. Right? That percentage isn't going to change. Doesn't matter what your sample size. So to make things easy, when we deal with percent composition, always say that you have, 100-gram sample. That way, if 40% of the composition by mass is carbon, and you have a 100-gram sample, then you have 40 grams out of 100. You have 40 grams of carbon, right? So in that case, here's what we're going to do. So we're going to take this particular one, and we're going to take, if it's 40 grams of 40% carbon, 6.7, this is the same one that we've done, right? Just assume that you've got 100 grams of it. That way, the percentages just turn to grams, because 40% of 100 grams is 40 grams, right? So the percentage drops out, and essentially you just change the numbers to grams. So the first thing we're going to do is we're going to find for each one, we're going to find the number of moles, and here we go, number of moles of carbon, 40 grams, which I got from my percentage. Molar mass of carbon, 12.01, 3.33 moles. 6.25 from my percentage, 1.01. Now remember, as we saw before, we're not adding the number different. We're not adding up the number of atoms in this particular case. It's just what comes out of the periodic table. 1.01 is the molar mass of hydrogen, 6.4, and then the molar mass, 53.3 divided by the molar mass over here of oxygen, which is 16, 3.34. Okay, so then I'm going to put the ratio of carbon to hydrogen to oxygen. This is kind of our new step. The stuff we just did there, we've done a whole bunch of times. So let's look at what we've got. We've got a ratio of 3.33 to 6.4 to 3.34. So we want to have a 1 to something ratio. So what we do is we divide all three by the lowest of the numbers, which is 3.33. So let's do that together. All right, so we're going to divide it by 3.33, all of them. And we end up with 1 to 1.92 to 1.001. Okay. So this is obviously, I'll just bring it over here so it's easy for you to see. This is obviously 1. And the last one, we're going to round that to 1 as well. Okay, now in the middle, 1.92. If you're 0.1 or less, because there has been some rounding along the way, okay, we always have a little bit of rounding as we do our calculations. 1.92, if it's less than 0.1, we're going to round it. So in this case, it is 2. And now that I've got that 2, this tells me my ratio of atoms. So the empirical formula is C1 H2O1. That's your empirical formula. So what we do is we find the number of moles of each, then create the mole ratio to get it in the lowest term so that we get divided by the smallest number, and then we get it into whole numbers because we can't have points, so we can't leave it 3 point. We can't have 3.33 carbon atoms. You either have a full carbon atom or you don't. So we can't have a percentage or a decimal. So we have to get rid of all those decimals. Remember, nearest, this is the lowest whole number ratio available to me. Okay, so there's the first one. I am going to do one more example for you. So the next one. Let's do if it's 35.4% sodium. Rest is nitrogen. All right, let me get my calculator ready as well. So if we're on to this particular one, just get my stuff in order here. And these are the ones just coming right out of the book, right? The rest here, hopefully we can figure out the rest, would be 64.6% nitrogen. So assume 100 grams. And then our first step is going to be number of moles of sodium, 35.4 grams, divided by sodium is 22.99 grams per mole. And I do my division, 1.540 moles. Okay, so there's the first step. Second step, number of moles of nitrogen, and equals 64.6 grams divided by 14.01 grams per mole. And that one is 4.611. Okay, got my number of moles of each one. Step 3, let's go to our ratio. And I always find it useful to write the ratio of what it is you're doing. I'm doing a ratio of sodium to nitrogen. So it's 1.540 to 4.611. Okay, 1.540 is the lower of the two numbers, so I'm going to divide both by that. That's going to give me a 1 to 4.611. 2.99. Okay, so 1.54 divided by 1.54 gives me 1. 4.611 divided by 1.54, 2.99. So it is 1 to 3, which means my empirical formula is Na. Yep. Got it in there, NaN3. Lowest whole number ratio. I just find that if you put the title sodium to nitrogen, then you always write sodium first, and then your nitrogen second. Okay? That's another example of how you go through it. So the steps are pretty much the same. Find the number of moles of each one. So take the mass, use that mass and the molar mass of whatever it is you're using to find the number of moles. And once you've got the number of moles, then you create a ratio, and that's our mole ratio. So I'll do one more here, 52.2% carbon, 6.15 hydrogen, and 41.7% oxygen. So you can see carbon, hydrogen, oxygen, we do those quite often. Hydrocarbons, very common. So first thing, assume 100 grams, because that's going to convert those percentages right into grams. Okay, and then we take the number of moles. So number of moles, that's my first step, number of moles, carbon. 52.2 grams divided by 12.01 grams per mole equals, again, it is an example from the book, but I'm just trying to, 4.3464. So just a brief thing about that, and there it is. The reason that we're carrying those extra digits in this is the less rounding we do, then when we get to the end and we divide our ratio, it'll be closer to a whole number. If you just make it 4.3 and you cut 464 off, that's going to make you further from a whole number when we get to the end. So we want to keep that together. Remember, it's only at the end of a question that our significant digits is something we have to make sure we have correct. So the number of moles of hydrogen is 6.15 grams divided by 1.01 grams per mole equals 6.0891. Okay. So again, just getting my mass, assuming 100 grams. If 6.15% of the compound is hydrogen, then I assume 100 grams, that means 6.15% of the mass is hydrogen. So I'm good through there. Again, carry those extra digits. And the last one is number of moles of oxygen, 41.7 grams divided by 16 grams per mole. Should be canceling my units out as I go here, which I didn't. I apologize for that one. This one is 2.6063. All right. Now I've got the number of moles of each one of my atoms. Okay, so step 4, I'm going to put them into a ratio. Step 4, ratio of carbon to hydrogen to oxygen is 4.3464 to 6.0891 to 2.6063. Here's my ratio. All I did was take the number of moles that I got in each of the steps 1, 2, and 3. And now I'm going to take this, I'm going to divide by the lowest value. So the lowest value is 2.6063. Divide all 3 by that number. 2.6063. And we get, that's a 1, obviously. This one is 2.29 and 1.67. All right, so there's my ratio. Now, those, I can't leave those numbers like that. So what we want to realize here is that you look for things, and this is where, if you're a really strong math student, I think it's on page 291 of the book. Look at your decimals and try and realize what fraction that is. So 0.67 is 2/3, or it's a multiple of 3. So with that particular one, when we want to multiply to get it to be a whole number, then we can use that knowledge in order to get it into a whole number spots. So we're going to multiply by whatever. In this case, if you multiply, I'll do it here with you, 1.67 times 3, it equals 5.01. Okay, and that's close enough to that 5. So what we're going to do is we're going to take right, so we're going to multiply them all by 3 in order to get whole numbers. That's what I put there. So what that does, this one's pretty simple. This becomes 5. And obviously this one becomes 3. Okay? Those are simple. So then take your 2.29 times 3 is 6.87. And 6.87, I'm going to round that to 7. Okay, it's a little, and again, because it's not a whole number, now obviously these would be whole numbers in nature, but they're not whole numbers because we've rounded here and there. And what that does, it gives me a molecular, or sorry, empirical formula of C5H7O3. Okay. So there's my empirical formula. Okay, that's my lowest whole number ratio that I can get. Now, the key here is just doing repetition because it's the same thing over and over and over again. We're trying to get the number. We're looking at mole ratios, and because those number of moles tell us exactly how many, what our subscripts are going to be in our chemical formulas. And these are empirical formulas, lowest number whole ratio. Later this week, we'll talk about molecular formulas and how they're slightly different, but you're going to do the exact same thing that you've done here. So we need to be able to do empirical formulas to move on. Okay, so I know a long video between the two. I probably won't post anything else until Thursday. The practice questions will be there. The notes will be there for you. So please continue to go through those. We're going to have, I'll have a quiz for marks. So those of you that want to raise that mark up from March 13th onward and to see how you're doing going forward, I'll put it on there. So again, the key is you got to do the work because all this stuff they're going to assume you know how to do in grade 12 for grade 12 chem. So if you are planning on taking 12 UChem, you got to make sure you know all this material. So if you do have questions, again, seems like Lucas is our designated question asker, but if you have questions, just put them on the Google Hangout. Just throw it on there and go, sir, can you do page whatever, number 3B? And I'll put the solution on, take a picture of it and send it to you. And if that's not enough, just ask for a video. Okay, gang, good luck with that. And again, I'm hoping that we get some videos or some questions to video and give you. And if anyone has seen or talks to Evelyn or Mackenzie, they're kind of missing in action right now. So maybe encourage them to get back on. Anyway, good luck and look forward to the questions. See you later.